All right, so we're going to be moving on to Chapter 22. And Chapter 22 deals with carbonyl condensation reactions. And the one we're going to be looking at in this video is the aldol condensation. And this one's actually not named after any scientist by the last name of Aldol. The word aldol actually comes from the words aldehyde that's then transformed into an alcohol. So they call it an aldol. All right. And the condensation implies that we're going to be removing water at the end. All right. So the aldol condensation is the transformation of an aldehyde into an alcohol, followed by the removal of water. All right. So the worst part of the aldol condensation is just kind of cutting down to a synthetically useful version of it. All right. There are a lot of compounds that can undergo aldol condensations. All right. And if you're not wise with your choices of reactants, you can have a complete mess on your hands. So one of the most synthetically useful versions of the aldol condensation is the Claisen-Schmidt variant. And what this one implies that you're going to be using a nucleophile that has only one enolizable position. All right. So that's going to cut down on what your nucleophile is. All right. If you had multiple enolizable positions, well, then you're going to have multiple places you can attack, and you're going to have quite a mess. Now, note that when I say one enolizable position, I'm talking about one unique enolizable position. So what I mean by that, if we had a acetophenone, this one works quite well. All right, because we can enolize there and only there. All right. If we use cyclohexanone, we're going to have an enolizable position there, but this is an identical enolizable position. So while there are technically two, we're only looking at the one unique enolizable position. All right. If we were to look at this molecule, we have two different alpha positions, so not good. All right. So you just want your alphas to be the same or only have one of them. All right, and the other guy we need in this reaction is the electrophile. And the electrophile needs to be an aldehyde. Those are the most electrophilic of the carbonyl-containing compounds that is used in this reaction. All right, so we like aldehydes. And you want these to have 0 enolizable positions. You don't want a competing nucleophile on your electrophile. All right. So if you lock these two in, you're going to have a very synthetically useful reaction. All right. So why don't we take a look at a pair that is quite useful. And go through the mechanism of this reaction. All right. So this is acetophenone. It's a ketone, and it's enolizable, and it's enolizable only at that one position, which I'm going to call carbon alpha. All right. And I'm going to react it with the aldehyde, benzaldehyde. All right. So benzaldehyde is a wonderful electrophile in the Claisen-Schmidt because it has 0 alpha positions that are enolizable. All right. So we're going to go ahead and say here is carbon A. All right. I'll put my lone pairs on here. And this reaction can be kick-started with sodium hydroxide. And you're going to get enolization in a reversible fashion. And you're making just enough of this acetophenone's enolate to get this reaction going. All right, so probably about 99:1 ratio of acetophenone to its enolate, but that'll be enough, and I'll explain why later. All right, so here's alpha, and attached to alpha is beta. All right, technically that's not a beta carbon. All right, but we're just using the Greek alphabet here. I'm going to call it beta for fun. All right, and then I'm going to have the aldehyde, which has carbon A, and I just made water. And I've got sodium coordinated to the O minus. So now we're going to get nucleophilic addition to the aldehyde. Remember, the aldehyde is electrophilic. All right, so I'm going to highlight that electrophilic carbon that's green. All right, carbon A is electrophilic. So we have a nucleophile in our enolate. So nucleophilic addition of the enolate will look like that. All right. So what we're going to be doing here is making a bond between the alpha carbon and carbon A. And we just need to keep track of all of these atoms in our product. That's the hardest part. And if you label the carbons alpha and beta on the nucleophile and A on the electrophile, and you can just get everybody attached that was attached to A, alpha, and beta, you're going to have much greater success. All right, so labeling is the key to getting this reaction product predicted correctly. All right, so I'm going from left to right. That was our beta carbon. Our alpha carbon had 2 hydrogens on it. And carbon A had a pH and an H attached to it. And I'm sorry, that's kind of sloppy. Let me see if I can clean it up. That is a negative charge on our oxygen. All right. So going back, what did we make our bond between alpha and A? All right. And just, look at that. Oops. And make sure you've got everybody attached to where they're supposed to be. All right. Again, we have what? Water. And sodium was coordinated. It doesn't matter where, just have it accounted for. And we're going to protonate our O minus in the product. So here's what we call our aldol. All right, so that is a product that happens. But in aqueous solution, all right, we form this, but it reacts immediately, all right, to form what we call the aldol condensate in an irreversible form, all right. So remember, there's hydroxide floating around that we just formed. So what it's going to do is it's going to grab an alpha proton, and then that alpha proton forms a pi bond between alpha and A. All right, we're going to get a double bond form there, and that is our elimination or our condensation step. All right, so condensation is the elimination of water in this case. So carbon beta is here. Alpha is there. We now have a double bond between alpha and carbon A. And carbon A lost the hydroxyl group, right? It's gone. And the only things left on carbon A is pH and H. All right? So what we have here is our molecule called our aldol condensate. It's the molecule that lost the water. All right, so there we have our 3 carbons, beta, alpha, and A all attached. All right, so how are we going to deal with this on a more complicated basis? So when you're asked, hey, this ketone and this aldehyde, what is the product that I'm going to get? All right, so how do we predict that? So we need to have a reliable method to where we can predict the products without having to go through that mechanism every single time. All right, so what I want to do is I want to take an example and ask, all right, what are we going to get when we react this aldehyde and this ketone together? All right, so I'm going to take this ketone here and this aldehyde here. Okay. So what we're going to do is we're going to try to figure out how this aldol condensation reaction is going to work. So first of all, do I have the right characters? All right. Well, this is an aldehyde, and it has no enolizable positions, right? Yes, that is an alpha carbon there, but those are methyl groups attached to that alpha carbon. So there are no protons to remove from the alpha carbon. So that is not technically what we're going to be looking for as enolizable, all right? Over on the ketone, we have an alpha position here, all right, enolizable. And if we draw an alpha there, yeah, that's an alpha position, but there are no hydrogens to remove to enolize on that side. Again, we have methyl groups there, all right? So that alpha doesn't count. So now we need to draw our letters, all right? So attached to alpha is the carbonyl carbon beta, all right? You always want to go towards the carbonyl carbon. In the case of a nitrile, you want to go towards the nitrile carbon as beta, all right? So you're moving towards the oxygen to get to beta. And then on the aldehyde, you always have carbon A, all right? So what does the product look like? All right, so going back to this, what carbons do we have in a row here? We've got beta, alpha, all right, and then A. So no matter what we're doing, we have these three carbons. So let's do them, beta, alpha, and A, all right? And we get a double bond that forms between alpha and A, all right? So you see that? Double bond between alpha and A. And then beta, well, what is it, right? And what else are we going to put in here? Well, all you got to do now is just put everybody that remains on these three carbons, all right? So beta, going in that direction, had a double bond to oxygen, all right? And then they're just part of this ring, right? Okay. And what did A have attached to it that we haven't accounted for yet? It had this tert-butyl group over here and a hydrogen, all right? So that's what we'll put here. Let me move this A out of the way. It's in a bad spot. Here. A hydrogen and our tert-butyl group, okay? So what have we lost in this process? We've lost water, all right? But nonetheless, this is our aldol condensate here. All right? So if you can just get those three carbons, the beta, the alpha, and the A carbon, all drawn, and then put everything else on there that you need, you should be good. All right, one more example. All right. So if I react these and then aldol condensation, all right, let's go ahead and start labeling. Aldehydes are always easiest to find for me, all right? So when I find the aldehyde, I just call it carbon A. And then I go over to the other molecule, which must be the attacking species, and I need to find the alpha carbon. And there it is, all right? So then I want to draw the beta carbon going towards the ketone there, So those are my three key carbons that I need to draw. So beta, alpha, and A. All right. Then it's up to me to put the double bond between alpha and A and then fill everybody else in. All right. So what did A have on it? All right. Remember, the oxygen's gone. It leaves as a molecule of water. It had a hydrogen attached to it. Okay. And then it had this ring, the methyl group in the para position. All right. So don't get confused or lost. Just remember, you're looking at A, and what the two groups that were left on A were is this hydrogen in this toluene ring system, if you will. All right. What's on alpha? Looks like we need what? The methyl group. Okay. You're asking, well, what happened to the two hydrogens on alpha? Well, remember, you've got to make what? Water? So where's water coming from? These two hydrogens that are gone and this O that's gone. All right. That's where the water is getting lost. All right. So you need to have at least two protons in the alpha position, all right, for this this condensation to work. All right. Okay, so beta has red, an oxygen and a phenyl group. All right, there you go. All right, that is the product of that aldol condensation reaction. All right, so one last example. You can use a ketone that has two identical enolizable positions. All right. All right, let's use this aldehyde here called furfural. It's one of the funnier names out there, but nonetheless, let's see if we can put this together. So this furfural has an aldehyde, and there's our A carbon. So what are we going to do here? Well, we're going to do what? Make a bond between alpha and A, and in this case, both our alphas are going to react. All right, so alpha and alpha makes bonds to what? A and A. Okay, and those are double bonds, right? So make a double bond between alpha and A, and we just got to figure out what the heck's left on A. The hydrogen and the furan ring. All right. Over here, the furan ring. All right, looks like a monster problem, right? But you can do this if you practice, of course, but if you just can label your carbons and remember what happens in the process, all right? So in this case, your alpha makes the bond to the A, all right? And you form that double bond between alpha and A. Don't lose track of beta, all right? And then just make sure you appropriately draw what is on all the carbons, A, alpha, and beta, all right? Good luck with this. Reach out if you have any issues. This is one of the more complicated reactions we go through, all right? But the aldol condensation is a very powerful reaction, used quite a bit in synthetic chemistry, and too bad we couldn't do it in lab this semester, but it's a fun one, all right? So, all right, well, next set of videos is going to contain two more condensation type reactions, and we'll be finished with this chapter. So take care, everybody. Goodbye.